We can now solve steady flow with simple and unsteady flow with pimple. But we've quietly assumed something false the whole time, that the flow is smooth and orderly. Real flow, at real speeds, is anything but. Turbulence is the hardest unsolved problem in classical physics. We can't afford to compute it exactly, so we model it. This episode is about what that means, and why it's a compromise you have to understand. Turbulence is swirling, chaotic motion, but the key feature is this: it happens across an enormous range of sizes at once. A big eddy the size of your whole domain feeds energy into smaller eddies, which feed still smaller ones, all the way down to tiny whirls where the energy finally turns to heat. This is the energy cascade. To simulate turbulence exactly, your mesh would have to resolve every eddy, from the biggest to the very smallest. And that is where the trouble starts. The honest approach is direct numerical simulation, mesh fine enough to capture every last eddy, and just solve the equations we already have. No modeling at all. The catch is brutal. The number of cells you need grows with the Reynolds number to the power of 9/4. Double the speed, and the cost explodes. For something as ordinary as a car at highway speed, that's trillions of cells and months on a supercomputer to simulate a single second. DNS is a research tool for simple cases, never everyday engineering. So DNS is correct but unusable for real work. We need something far cheaper even if it costs us some exactness. The workhorse of engineering CFD is RANS, Reynolds averaged Navier-Stokes. The idea: don't track every wiggle. Split each quantity into an average plus a fluctuation. Velocity becomes a steady mean plus a fluctuating part. We then average the whole equation set, and solve only for the mean flow, the smooth part an engineer usually cares about. Instead of chasing the jagged red signal, RANS solves for the smooth teal average. Vastly cheaper, a normal mesh, a normal run. But averaging comes at a price, and that price is the whole story of turbulence modeling. When you average the equations, something inconvenient falls out. New terms appear, and this should feel familiar from the simple episode. These are the Reynolds stresses, the leftover influence of all those fluctuations we averaged away. They represent how the turbulence stirs and mixes the mean flow. And here's the trap, exactly like pressure back in episode 8. These new unknowns have no equation of their own. We have more unknowns than equations. The system isn't closed. That's the closure problem. And the fix is the same philosophy as before: if the equations won't give us the missing quantity, we supply it with a model. A turbulence model is exactly that closure. Most turbulence models use one clever idea: treat the turbulence as if it adds extra, effective viscosity and eddy viscosity that thickens the fluid wherever it's turbulent. Two models dominate engineering. K-epsilon solves two extra transport equations for turbulent energy K and its dissipation epsilon. It shines out in the open flow, it's robust and cheap, and it's the classic default. K-omega SST blends two models to behave well right next to walls and when the flow is about to separate. For aerodynamics and most external flows, it's the modern go-to. If in doubt, people reach for SST. Now the practical part that trips up almost everyone: Y+. It's a non-dimensional measure of how tall your first cell is, right next to a wall. Why does it matter? Because velocity changes violently in the thin layer right at the wall. Your turbulence model needs your first cell to sit at the right height in that layer, or its answer for drag and heat transfer is simply wrong. There are two valid choices. Use wall functions and keep Y+ around 30 to 300, coarser and cheaper. Or resolve the wall directly with Y+ near 1 many fine cells, but accurate. The mistake is landing in between, where neither works. Check it with the Y+ utility after every run. One more name you'll hear: LES, Large Eddy Simulation. It sits between DNS and RANS. LES resolves the big, energy-carrying eddies directly, like DNS, but models only the small ones, which are more universal. It's far more accurate than RANS for unsteady, swirling flows. It costs far more than RANS and far less than DNS. You reach for it when averaging throws away too much combustion, acoustics, strong unsteady mixing. For most steady engineering, RANS still wins on cost. So what does all this look like in your case? Two things. First, constant/turbulence properties picks the family RAS for RANS and the specific model, like k-omega SST. Turn turbulence on, and OpenFOAM adds the closure to your momentum equation automatically. Second, you supply new fields in the 0 folder, k, omega, and the turbulent viscosity net, each with the right wall boundary conditions. That's the whole setup. The theory you just learned is why those files exist. That's turbulence modeling, and that completes phase 2. You now understand what's happening inside the solver, the simple and pimple pressure velocity loops, and why turbulence must be modeled rather than solved. The black box is fully open. From here, everything changes gear. You've built the mesh, set the physics, understood the solver. Phase 3 puts it all to work on real engineering, flow around a body, heat transfer, and a case drawn from right here in the Kathmandu Valley. Next up, external aerodynamics. See you there. We can now solve